All right, so I'm going to start with a basic lecture on Riemannian geometry. So I'll talk this morning. Tian will talk in the second half, and I believe do Kähler geometry. And then tomorrow, or not tomorrow, Wednesday, I'll have a second lecture on the Ricci flow in the Riemannian case. And then I imagine Tian will talk about the Kähler case. So I'm going to start with a review of connections, geodesics, Gauss map. So the local theory of Riemannian manifolds, and then talk some about curvature, Riemannian curvature, and its relation to the Gauss map to geodesics. Then I'll talk about some of the more global aspects. Homogeneous Riemannian manifolds. Homogeneous surfaces and homogeneous Riemannian manifolds. And then I'll finish today with a brief discussion of various kinds of geometric limits. So limits of Riemannian manifolds. Both smooth limits where everything is converging and more singular limits called Gromov-Hausdorff limits. So that's my plan for this first 45 or 50 minutes. All right. So the basic object under consideration is a Riemannian manifold. So it's some smooth manifold of a dimension that's not too important right now, and then a Riemannian metric. So G is a positive definite Riemannian metric. If I write it out in local coordinates, if I have local coordinates on the manifold, then the metric is given as a symmetric matrix. The Gij, symmetric. These are smooth functions of the manifold. They make at each point a symmetric, positive definite matrix. So that's a Riemannian metric. Now the basic geometry built out of this metric involves the connection, the metric connection. G. Sorry? This?
Yes, and pi I. Gij.
Gij and okay. So I want to talk about the connection associated to this metric. So this is a pairing from vector fields on the manifold, in fact, even local vector fields, back into vector fields. And we usually write it this way. We write one of the indices, the first index, as a subscript, and the second index we think of, this is an operator depending on x applied to a vector field y, so this is another vector field. Right. And the basic properties that this connection is required to satisfy is, first of all, it's in this variable, it's linear over the functions. Which is simply the equation that if you differentiate with respect to f times x in the fx direction, you simply get the value of the function. The function pulls out. All right, so that's linearity over the function in the first variable. It's not linear over the functions in the second variable. It acts as a derivation over the functions in the second variable. So that's the equation that, well, you have the term that you would expect, linearity over the functions, but then there's a second term, the vector field acts as derivations on the functions, and then that multiplies y. So that's the derivation law in the second variable. So it's completely linear over the functions in the first variable and satisfies this derivation law in the second variable. It's supposed to be a metric connection, so it preserves the metric in the following sense. If you take the inner product of two vector fields and differentiate that in the x direction, so this is a function you can differentiate using a vector field, that is simply what you get by applying the covariant derivative in the two factors and taking the inner product. Now, the way to think about this is really that the covariant derivative of the metric is 0. Think of this as a cubic operation. The bracket is really secretly multiplying by the metric gij. So you have three variables, y1, y2, and the metric, and you would expect when you differentiate, you'd get three terms. You differentiate the first vector field, you differentiate the second vector field, and you differentiate the metric. And this is saying that third term doesn't appear, which is the equation that the covariant derivative of the metric is 0. And then the last property, which I'll write over here, is, to me, the most mysterious.
Define how x on
Yeah, I haven't. I'm not going to. I'll leave that to your imagination. Yeah, so the point that Fadeev is making is that one extends from vector fields to tensors of higher order. This metric is a symmetric two-tensor, contravariant two-tensor rather than a covariant tensor. And I have to extend the connection to all tensors, and then this equation makes sense. And the last, to me, is a completely mysterious condition. I don't understand it geometrically, but algebraically it's a beautiful condition. It's the torsion-free condition. And it says that if you take the difference of the covariant derivatives in the two orders, you switch the variables, you simply get the Lie bracket of the two vector fields. Now there's a generalization of this theory of connections in a more general context of vector bundles or principal bundles. And in that more general context, this first variable is always a vector field. That's the direction in which you're differentiating. But these things now become sections of the bundle in which you're doing the differentiation, and the answer lies back in the sections of the bundle. So this is the vector fields, this is sections of the bundle, sections of the bundle. These two rules still make sense. This one has no meaning in that context. So this is an equation you can only write down when both the differentiation direction is a vector field, as it always is, and what you're differentiating is a vector field. So this is special to the tangent bundle.
Is the geometric meaning of the third condition?
Sorry?
Is there geometric meaning?
Yes, well, as I said, I don't understand the geometric meaning of this. Yeah. This has always been a very mysterious condition as far as I'm concerned. Maybe real geometers, and I'm only a topologist, so this is beyond me. Maybe real geometers understand what this means. Maybe Tian can tell us. But I don't have a good picture of what this means. But there's then a beautiful theorem which says that given G, there exists a unique connection satisfying 1 through 3. And it's called the Levi-Civita connection. metric determines a connection with these three properties. In local coordinates, we've written the metric as a symmetric matrix, Gij. The connection is written as in terms of the Christoffel symbols. And the formulas for these are simply, you have, again, local coordinates, x1, xn. Those are coordinates on the manifold. They also give you a basis of vector fields, the partial derivatives, in the coordinate directions. So whatever open set U these coordinates exist on, this gives you a basis at every point for the tangent space. And then the Christoffel symbols are simply the covariant derivative in the ith direction of the jth partial derivative is gamma ijk partial k with the Einstein summation convention. Okay. So these are a triple of C infinity functions, and these rules, well, this one tells you that you only have to know the partial, well, these condition one tells you only have to know you only have to know the value of the connection when x and y are partial derivatives in order to determine it everywhere. So the gammas completely determine the connection by formula one. Formula three says that since the bracket of these vector fields is zero, it is a symmetry condition in the gammas. Sorry. Right. So the gammas are symmetric in the lower two indices. And the third, in the second condition, is a relationship between the gamma ij's and the metric, which is pretty easy to write down. I won't actually do it. And then it's a nice little algebraic fact that completely determines the gamma ij's, that equation involving the metric and the symmetry condition. So that's the local formula for, you in fact write down a local formula for the Christoffel symbols, these gamma ij's, in terms of the metric and the first derivatives of the metric.
So it is unique locally, and roughly speaking, the apoids, how to say, can be glued. The apoids can be glued together over the domain.
That's right. This is a local expression. This is an expression in terms of local coordinates for the covariant derivative. It completely determines the covariant, the covariant derivative is given by these in these local coordinates, and there's a formula in those local coordinates for the connection. Yeah, and then it transforms correctly, as you say, so that gives you proof of the existence and uniqueness. Okay. Now, out of the connection, we build the geodesic equation. So this is an equation for a curve in the manifold. Okay. And so if you have a curve at each point, you have its tangent vector. So at each point along the curve, we have the, this one works better? Thank you. In the tangent space to the manifold at the point along the curve, its first derivative. And the geodesic equation is that the covariant derivative in the direction of the tangent vector of the tangent vector is 0. Now this actually requires a little explanation because these are not vector fields. These are only vector fields along a curve. So what you do actually is you extend these partial vector fields, a vector field along the curve, arbitrarily to a smooth vector field in a neighborhood of the curve. Then with those extensions, you write down this equation and you restrict it to the curve, and it turns out when you restrict this equation to the curve, you get something that only depends on the value of the vector field along the curve. So you write the equation this way. And in fact, in terms of the Christoffel symbols, this equation is a second order equation again in my local coordinates x1 to xn, these are now functions of t. So locally, my curve is given as x1 of t up to xn of t. Its first derivative, its tangent vector, is of course just the first derivatives, given by the first derivatives of the coordinates as a function of t, and the geodesic equation becomes a second order equation, a linear second order equation. Okay? So there's at least locally, an existence and a uniqueness if you specify an initial point, gamma of 0, and an initial tangent vector, gamma prime of 0. There is a unique geodesic satisfying the geodesic equation, unique, defined in some neighborhood. To solve that ODE. Okay. This allows us to define the Gauss map, which is a map, a smooth map defined at least in a neighborhood of the origin, the tangent space, the manifold at a point. So this linear space back to the manifold. As I say, it may not be, in general, globally defined, but it's defined on some neighborhood of the origin of some size. So a ball around the origin of radius epsilon, you have the exponential map. And it's simply the map that takes any radial line in this vector space and sends it in the manifold, here's the manifold down here, to a geodesic running at constant speed, speed 1, starting at this point x, and with this as initial tangent vector. Okay. So this is a mapping, if you think in terms of the sphere, it will be a standard sort of mapping that sends every straight line in the tangent space down onto a piece of the great circle moving around the sphere. And that turns out to be a smooth mapping. Usual sort of smooth variation of solutions of a ODE in terms of the initial conditions. So that's the Gauss map, and we will come back to this map a little bit later when we have curvature and start understanding a little bit more about it. Okay, so that's the first order theory. The metric is, if you will, zeroth order. The connection involves differentiation. It's a first order theory. If you ask, well, now we're going to study the second order theory, which is curvature. So the Riemannian curvature. There are many ways to understand why curvature is so important. One of them is that, so if you write down a metric in local coordinates, you can ask, what are the geometric properties of the metric? What are the properties of that smoothly varying collection of matrices independent of the coordinates you use to write it down? So for example, at a point, there's no information at all. All metrics at a point are equivalent. This is a standard fact about positive definite inner products on a Euclidean space. They're all the same up to linear change of the Euclidean space. So given any positive definite matrix on a vector space of dimension n, you can find a basis for the vector space in which that inner product is diagonal with diagonal values 1. So it's the standard inner product. Well, you can take that statement, that linear statement, and transform it to a statement about metrics. So given a metric in the neighborhood of a point in a manifold, and you ask what information is there in the value of the metric at a point, and the answer is none. You can change the local coordinates reflecting the linear change you need to make. so that at this point the metric looks exactly like the standard metric. Okay? Well, can you do better than that? Can you make the metric standard to second order, third order, infinite order? Turns out the answer to those questions is contained in curvature, and in the end, locally at least, these are the only geometric invariants of the metric. So if you have two metrics locally and you want to know are they the same or not, the answer resides in the curvature. If you have a local diffeomorphism between the manifolds that pulls the curvature tensors back, it's in fact an isometry. Or said another way, as we'll see, you can use the metric, well, I'm not going to prove it, but I'll state it. You can use the metric to write down a formula. You can use the curvature to write down a formula for the metric in Gaussian coordinates. So at least locally, the Riemannian curvature tensor tells you everything about the metric. It's geometric quantities, the quantities independent of the coordinates you use to write it down. Okay. All right, so curvature. Curvature has to do with the fact that in this context, second derivatives don't commute. All right, so in fact, the curvature, I'm going to define it as a function of two vector fields. Okay, so that's the formula I write down. I mean, ignore this for just a moment, or work in a basis and use the x and y as partial derivatives of the coordinates, so that in fact the bracket it vanishes. So what we're really doing is studying the non-commutivity of second derivatives as applied to vector fields. If I were to apply if I were to apply x and y to functions, then I would get, and think of covariant derivative as just the usual derivation of a function with a vector field. In that context, this difference is the definition of the bracket. So this expression will vanish when applied to functions. If you allow me to extend covariant differentiation to all tensors back to functions by the usual derivation law. So now we're asking what happens when you apply these covariant first order derivatives, covariant differentiation, to vector fields instead of to functions. So this is a map from the vector fields on the manifold to the vector fields on the manifold. Okay. Well, you do several computations and you see that, how should I do? Oh, I see, I can do this, can't I? Oh, no, I can't. You see that the first little lemma is that this expression is tensorial, that is linear over the functions, in both x and y. So it's linear over the smooth functions on the manifold in x and y. So in other words, if you, and well, let me say this, it's clearly skew in x and y, skew symmetric in x and y. If you switch x and y, changes sign. So linearity over the functions is, because of skew symmetry, I can just think about linearity in the first variable. And it's the equation, which of course means that if you apply it to any vector field z, you get an expression like that. Now this isn't completely obvious because, well, when you look at it, this term will be linear over multiplication by a function because the derivation with respect to x is the last thing you do. And so it's linear over the functions. Here, however, you get another term when you expand this out because you get the linearity over the function here, but now you have to differentiate with respect to y. So there's an extra term, y applied to f. But that's exactly what appears here. So you just write this out, and you see it's linear over the functions.
Does this lemma mean that, or implies that R is a tensor?
That's right.
So it is a section of just vector bundle.
That's right. So this makes R tensorial in X and Y. That's right. But it's even better than that. It's also linear over the functions in Z. So what this means is that we can think of this object and, okay, so now I want to form a 4 tensor. So I have something tensorial in 3 variables, but the answer is, the result of this operation is in another vector field, and I want to get, well, okay, so I want to consider the following. R, X, Y, Z, inner product with W. So this is something that depends on 4 vector fields, and it is linear in the functions over this one, obviously. These two, that's what I just said, and this one. So this is linear over the functions in all 4 variables. So this is a 4 tensor. And what sort of 4 tensor is it? Well, you usually write it this way. R, I, J, L, K is by definition, well, with the Einstein summation convention, this thing is R partial I partial J applied to partial K, no, applied to partial L evaluate, sorry. I still don't have it right. That's what I mean. Right. So if you take the curvature and apply it to partial I partial J, that gives you an endomorphism of vector fields. Apply that endomorphism to partial K, you get a new vector field, and that vector field is written in terms of these. So that's the definition of Rij Lk. Okay. And now we have a 4 tensor. And this is the 4 tensor of Riemannian curvature. So, and then we define in the usual way RILK to be RIJMKGML. The usual way you raise and lower indices. And this is simply R partial I partial J applied to partial A, L inner product partial K. And that's a 4 tensor, and the tensorial structure is given in the way you write this, LK dxi wedge dxj. That expresses the skew symmetry in the first 2 variables. It turns out simple computation shows you it's skew symmetric in the last 2 variables. And it also turns out, because of the torsion-free condition, to be symmetric in interchange of this pair. So this is a symmetric 2 tensor on wedge 2 of the cotangent bundle. Well, or symmetric 2 tensor on wedge 2 of the tangent bundle.
Is it a kind of unique tensor with certain property there?
Yes. Now, what are the properties? Non-commutativity of the second derivatives. Well, let me say what it is in case of surface, okay? This predates Riemann. It goes back to Riemann's thesis advisor, Gauss. So Gauss was studying, I guess, first of all, surfaces in 3 space, and he defined the Gaussian curvature of a surface at a point in terms of an area defect. So again, we have the Gauss map, so you can look at the ball centered around this point P of radius epsilon, and you can ask about its area as compared to the area that you would get in flat space, which is pi epsilon squared. So take the area discrepancy between flat space and your Riemannian surface, your surface. Well, let me write it over here. Pi epsilon squared minus the area of the ball centered. Okay. This turns out to be fourth order in epsilon, at least as epsilon goes to 0. And I can't remember if the constant's 12 or 24. Does anybody know? 12 or 24? I did a computation last night. I got 12, but I sort of remember 24, so I'm not sure. This is the Riemannian curvature tensor. Well, this is the definition of the Gaussian curvature at the point. Okay? So it tells you how much area to the next order in epsilon you have compared to the flat area. And this is also, if we think of a surface with a metric, wedge 2 of the tangent bundle is identified with the line up to plus minus. So then this Riemannian curvature is a map from the line to the line, so it's multiplication by some number. That number is the Gaussian curvature. Okay? So now in a higher dimensional manifold, in any two-dimensional direction, you can put in a surface tangent to that two-dimensional direction, compute its Gaussian curvature, and you will get then the Riemannian curvature of that two-plane applied to the two-plane. So the value of the Riemannian curvature, the diagonal value on that two-plane. So that's the geometric property. So it's clearly, from that description, a geometric invariant of the metric. I didn't need any coordinates to write it down. Well, I didn't need any coordinates because I wrote a formula in terms of covariant differentiation. Okay, so that's the Riemannian curvature. Let's go back to the Gauss map. And fortunately, I'm completely out of time, so I can't do this computation because I was trying to do it this morning and I couldn't make it work out. But there is a formula in terms of the Riemannian curvature tensor, which I'll call Rm, for the pullback under the Gauss map of the metric. Okay. So we have our manifold, our smooth manifold. We're concentrating attention on a point, and we write down arbitrary local coordinates, x1 to xn, smooth coordinates near this point. And once we do that, we get a metric, which depends on the coordinates we've chosen. But now we're going to pick nicer coordinates, the Gaussian coordinates. So we go to the tangent space at this point, and we choose an orthonormal coordinate system on the tangent space. After all, we have a metric, so an orthonormal coordinate system makes sense. And then so that gives us a Euclidean set of coordinates up here on the tangent space, and we exponentiate from some ball around the origin in Euclidean space down onto the manifold. That's a smooth map, at least near the origin, and we can pull the metric back. Let's call it G, and we get some metric G hat on this neighborhood of the origin in Rn, and there's a formula for G hat in terms of the Riemannian curvature tensor. And by the way, G hat is the identity to second order at the origin, and its second derivatives at the origin are given by the Riemannian curvature tensor at the origin. So the answer to the question, how standard can you make the metric, is, in general, only up to second order at a point, and then the curvature prevents you from doing any better. Okay. So this shows you that at least locally, the geometric properties of the metric, in other words, the metric up to the action of change of coordinates, or the action of the diffeomorphism group, is simply the Riemannian curvature tensor. So for example, you could ask the question, when is there a local coordinate system in the neighborhood of the manifold so that the metric looks like the standard Euclidean metric? And in other words, is a standard flat metric. And the answer is if and only if the Riemannian curvature tensor vanishes throughout that neighborhood. Okay? All right, well, that was the local theory. You have to move a little quicker on the global theory. Now, the statement that I just made about, let me say one more thing about curvature before I leave, because this will be very important for what comes later. There's a tensor associated to the Riemannian curvature called the Ricci curvature. In local coordinates, it's Ricci ij dxi tensor dxj. So it's a symmetric two-tensor. And it is defined out of the Riemannian curvature tensor, which is a four-tensor. Remember I told you it was skew in these two variables, and symmetric under this interchange. And the Ricci tensor is determined from the Riemannian tensor by tracing on these middle two variables. So in local coordinates, Rij is simply GKL RIK LJ with the Einstein summation convention. So this this symmetry of the Riemannian curvature tensor implies the symmetry of the Ricci tensor, and this is, as I say, a symmetric two-tensor. Let me not say anything more about that right now. So let me go back to this question of to what extent the metric is determined by the curvature. So we've said that locally that's completely true. Up to change of coordinates, or the action of the diffeomorphism group, the metric is completely determined by the curvature. We can ask, is that true globally? And of course the answer is no. So there are more global invariants to a Riemannian manifold And let me start with a simple example that I'm sure is known to all of you, flat surfaces. Now I'm going to take closed ones, compact. So when I say flat, I mean the Riemannian curvature tensor is 0, so locally at least the surface is modeled on R2 with the metric. And in fact, if you take this flat torus and you take its universal cover, well, we know topologically that's R2, but in fact the induced metric is the Euclidean metric. So on the universal cover, the induced metric from this flat surface is the standard, up to change of coordinates, is the standard Euclidean metric. And so what happens is the fundamental group of the torus, which of course is also its first homology group, is then embedded in R2 as a lattice. That is a free abelian group of rank 2 embedded as a discrete subgroup of the additive group R2, and the torus, so that's a lattice lambda, and the torus is isometric to the Euclidean space divided out by translations by the lattice. And now you're reduced to studying questions about lattices in R2, and well, the standard theory tells you, so this lattice has a basis V1 and V2, and let's make our manifolds oriented. And if I do that, then in the plane, there'll be a counterclockwise rotation from V1 to V2. That's the orientation convention. And so if I use complex coordinates on this R2, I can write V2 as tau times V1, tau in the complex numbers. Of course, it's just the complex number that's its length is the absolute value is the ratio of the length of V2 to the length of V1, and its argument is the angle between V1 and V2. So tau, in fact, is not only in the complex plane because of my orientation conventions, it's in the upper half plane. This depends on a basis I've chosen for the first homology, and I can change that basis by an arbitrary 2 by 2 integer matrix of determinant 1. So I really get the class of this element in H2 modulo the action of SL to Z. So the upper half plane divided out by the action of SL to Z is an invariant of, the point in there is an invariant of this flat torus. If you want to know what this thing looks like, it's something called the J function, which maps it isomorphic to the sphere minus infinity. So I have a sphere's worth, minus 1 point, of flat tori, and I also have an element in R plus, which is the area of the torus. And those two turn out to be complete invariants of flat tori. So we have a real three-dimensional space of these flat tori. They all have the same metric. In the sense you write in local coordinates, it's a flat metric. So you have these moduli spaces, or continuous finite dimensional spaces of manifolds with a given local metric structure. Okay. Now, if you move on from the torus to surfaces of higher genus, situation is even more interesting. The nice metric to write down on a surface of higher genus is a homogeneous metric based on the upper half plane, again the same upper half plane, but this time thought of as the model metric space. So we take the upper half plane inside C, imaginary part greater than 0, and we take the metric in terms of the standard Euclidean coordinates given by this. Okay. That turns out to be, sorry. There's a tensor here, right? Thank you. So this metric turns out to be invariant under the action of real 2 by 2 matrices, which acts transitively on the upper half plane. So this metric has the same curvature tensor everywhere. Well, we're back in the case of surfaces. So curvature is this Gaussian curvature. It's a number, sectional curvature on the standard orthonormal 2 plane, and that the curvature of this surface is everywhere minus 1. So it's a negative sectional curvature, constant negative sectional curvature, replacing the flat or 0 curvature we had just a minute ago. And it turns out if you have a surface of genus greater than 1, 2 or more holes, it has a metric which locally is isometric to this metric on the upper half plane, the Poincare metric on the upper half plane. And in fact, in that, so if you have such a metric, in that context, the universal cover as a Riemannian manifold is the hyperbolic plane, and this time the surface is represented as, well, is given by a discrete subgroup in PSL2R. And families of such metrics, there are families of such metrics as you can vary this subgroup, and it turns out you get a complex 3G minus 3 or a real 6G minus 6 dimensional space of such metrics. So once again, we see moduli spaces, finite dimensional, 6G minus 6 dimensional families of metrics with a given curvature or a given local Riemannian structure. Okay. There's a nice picture of what these, well, maybe I don't have time to say that.
This is so-called modular space of algebraic curves of genus G.
That's right.
Riemannian surfaces.
That's right. That's right. So it turns out that if you have a complex curve, a real two-dimensional thing with a complex structure, its universal cover is conformally equivalent to the upper half plane. So you can then put on a metric, so you can associate to that complex surface a unique metric of constant curvature minus 1, which is conformally equivalent to it. And then you get a point in the space as I've described it here. That turns out to be an isomorphism between complex curves up to the automorphisms and these up to the automorphisms, right? Now there's something very special about dimension 2 here. I just want to point this out. There's an analog of the upper half plane in every dimension. It's the complete simply connected hyperbolic space in dimension n. It's given as a hypersurface in the quadratic form with one positive eigenvalue and all the rest negative, the one the physicists are so fond of. It's a level set in there. It's a hyperbolic in space. It has a metric analogous to this one, hyperbolic constant curvature minus 1. So there's a basis in which the Riemannian curvature is, an orthonormal basis, is diagonal with all sectional curvatures minus 1. Every sectional curvature is minus 1. And one analogous to what you do for surfaces can form hyperbolic manifolds in higher dimension by dividing out by discrete torsion-free subgroups. Unlike this case, once n is at least 3, the group completely determines the geometry. This is called Mostow rigidity. So in the case of surfaces, we fix a group, the fundamental group of a surface of genus G, and we have a 6G minus 6 dimensional space of these hyperbolic metrics. You go to dimension 3, you fix the fundamental group of the 3 manifold, and you ask how many hyperbolic metrics can we have on this 3 manifold? The answer is 1 at most. And that rigidity statement is true in all higher dimensions. It works not only for these homogeneous spaces, it works for all other homogeneous spaces. As you go through all homogeneous spaces, the only counterexamples are Riemann surfaces. All right, have I run out of time, or do I have 5 more minutes? Yeah, which? 5 more minutes? Okay. So these are the nice metrics on surfaces, and this picture of homogeneous metrics has a generalization in higher dimensions. It just diverges from all possible Riemannian metrics. There are in each dimension the nicest Riemannian manifolds, those that are homogeneous, those that have a transitive, whose universal cover has a transitive group of isometries. But most manifolds don't admit those kind of metrics, and I'll talk when I do Ricci flow in the second part. I'll talk about dimension 3 and where it's not true, but it's almost true. In higher dimensions, it's far, far from being any relationship. I wanted to finish with the 2 notions of limits that are very important in studying these manifolds: geometric limits and Gromov-Hausdorff limits. So let me start with geometric limits. So I'm imagining a sequence of Riemannian manifolds with a base point of a fixed dimension. Okay. Dimension is K, the sequence is indexed by n. So I have a collection of based Riemannian manifolds. I want to define the notion of this sequence converging geometrically to a limiting manifold with a limiting Riemannian metric and a limiting base point. Okay. Now, in this notion of geometric limit, the topology of the manifold can change. So for example, these might all be a fixed manifold with a varying family of metrics or a varying family of base points, and this limit could look very different, of a different topology. These might all be compact, this might be non-compact. So let me give you an example of a geometric limit, and then I'll give the definition. So let's take any Riemannian manifold in Mn and any point. Okay. So that's our initial data. All the manifolds are going to be the same. All the points are going to be the same. But the metrics are going to be multiples of the given metric by a sequence of constants going to infinity. So I'm taking one fixed Riemannian manifold and a fixed point in it, and I'm simply scaling it up, making it bigger and bigger and bigger to infinity. Then the geometric limit. Anybody want to guess what the geometric limit is? What's happening to these manifolds as you make them bigger and bigger? Yep. It converges geometrically to the tangent space of the original manifold at X with the induced metric. So these manifolds are just getting flatter and flatter, further and further out. Okay. So you see the topology's changed, right? This might have been the round sphere to begin with, and suddenly it's converged geometrically to a Euclidean space. Okay, so now the definition. The definition is, the idea is that arbitrarily large but compact subsets in here have to be better and better replicated back here. So I won't say it in terms of compact, I'll say it in terms of open sets. So you have a sequence of open sets in the limiting manifold, increasing sequence, and an exhausting sequence. And they all contain the base point. So in the limiting manifold, whatever it is, you have this limiting base point, and you have this bigger and bigger sequence of open sets, which you could take to be balls of larger and larger radius around this point if you wanted, but some sequence of open sets. And for all n sufficiently large, we have an embedding of the nth open set back into Mn. Smooth embedding. And sends the base point to base point. And the metrics converge when pulled back. Now this convergence, of course, means uniformly on compact sets. If you take any compact set in M infinity, it will eventually be in all these Un, and therefore I can restrict these metrics that are all defined on Un, and therefore on that compact set. And on that compact set, these metrics are converging uniformly to G infinity. Okay? And if you take this definition and you work out this case of blowing up the metric, you can easily prove that these metrics converge to the metric on the tangent space. I'll just draw two other pictures to give you an idea of what happens. Think of hyperbolic surfaces. It's the hyperbolic surface of genus 3 with a long, thin neck. And the sequence of manifolds, in this sequence of manifolds, it's all going to be hyperbolic metrics on the surface of genus 3, but the neck's going to get longer and longer and thinner as I go along. If I put the base point over here, then I'll get a limit, which is a non-compact hyperbolic surface with one cusp in genus 1. If I put the base point over here, I get a limit, which again is a hyperbolic surface with one cusp, but it comes from this side, so it's got genus 2. If I put the point here, then I have trouble. And the reason I have trouble is they're very short loops. This part of the manifold is collapsing. So I can't take a geometric limit at a sequence of points like this, but I can take a weaker limit called the Gromov-Hausdorff limit. And anybody imagine what this thinner and thinner sequence of arbitrarily long tubes converges to?
The cusp.
Well, which side?
To both sides.
And both sides would then be what?
Line.
There you go, a line. It's becoming one-dimensional. So this is not a smooth limit in any sense. The dimensions changed. In geometric limits, clearly the dimension is constant. So this sequence of Riemannian surfaces based at this point is converging in some kind of sense of metric spaces to a line. And that's Gromov-Hausdorff convergence.
Does it somehow related to the notion of Alexander space?
Yes. The notion is, if I had, I mean, I'll talk about this next time, but there is a condition on Riemannian manifolds that implies that there will always be a Gromov-Hausdorff limit of a sequence of, say, fixed dimension. And that condition is that you have the curvature condition in an Alexandrov space. The curvature is bounded below by some constant, positive or negative. So you have a sequence of compact Riemannian manifolds with curvature bounded below. There will always have, that sequence will always have a Gromov-Hausdorff limit, but it will not. Sorry?
Partially, subsequence.
Yeah, of course. You have a Gromov-Hausdorff limit, and that will be an Alexandrov space with the same lower curvature bound. So Alexandrov spaces occur when you compactify this collection of Riemannian manifolds. If you don't put a lower curvature bound, at least on the Ricci curvature, you can't in general take a limit. Right, so that's how it's related. All right, well, I'll stop here.